In this assignment, you will use the Fourier convolution theorem to implement Poisson image blending in the Fourier space and avoid matrix inversion in the spatial domain as described in lesson 6. As always, there is a project notebook and a solution notebook, the links to both of which will be provided in the description of this video. Let's open the project notebook. So this is a toy example. Here the image is, this is the source image. All it is a white square against a black background. And for simplicity, we're not going to worry about masking. We want to use the Poisson formulas to go to transfer this image from the source image to the target image. So the first thing you do is you compute the right-hand side, which is B, and that's the Laplacian of this image. This is the Laplacian kernel. You compute B. Next, you take the Fourier transform of B, and you can use the NumPy's fast Fourier transform to achieve that. And then there's a test cell that tests your implementation. And next you move on to computing the diagonal matrix, which we call lambda k. And to do that, you have to recall that kx are the frequency indices in the range m, ky are the frequency indices in the range n. And so you use a mesh grid to create a grid for these range of frequencies. And then you populate that grid by applying this formula. And then we have a test cell that tests your implementation of the diagonal matrix. Now that you have both the diagonal matrix and the Fourier of the right-hand side, you can simply divide them together and take the inverse Fourier of that to solve for f. That's what you do here. We'll test that implementation. And finally, there's a function that will help you visualize all of this.